Wrinkles play a crucial role in the realism of virtual garments. They reveal how fabric bends, compresses, and interacts with the body, and are essential for high-quality results in games, AR, and digital fashion. Physics-based simulation can generate high-quality wrinkles and fine fabric details, but the computation is too slow for real-time applications. There are multiple neural approaches, but they often lack realism and depend heavily on large training datasets. Self-supervised garment simulation offers a promising alternative. It removes data requirements and enables fast inference. However, current methods still overlook persistent wrinkles, which are caused by the fabric's plastic behavior. In this work, we propose a new physics-inspired curriculum learning scheme that gradually shifts the material behavior from purely elastic to elastoplastic, enabling our model to capture the fabric's plastic behavior and produce realistic persistent wrinkles. We make three main contributions. First, we introduce the first self-supervised learning framework that can learn garment dynamics with persistent and physically plausible wrinkles, without relying on pre-generated simulation data. Second, we propose a novel neural network trained through energy minimization, which incorporates a dynamic bending energy formulation to model multi-phase plastic behavior in garments. And third, we develop a physics-inspired curriculum learning scheme that gradually transitions the training from purely elastic behavior to fully elastoplastic dynamics, enabling stable and physically meaningful learning. Our model is built with two cooperating networks, the elastic network and the plastic network. To generate persistent wrinkles, we treat the garment as having a rest bending state that can change over time. The ENet predicts how the garment deforms under body motion, given the current rest bending. The PNet learn to predict this rest bending, which is then used by the ENet for deformation prediction. During training, the two networks operate in an alternating loop. We start by initializing the rest bending to a near zero value. The ENet predicts the garment deformation, which is then used to compute the training target for PNet to predict the rest bending. The PNet then takes the current garment state as input, and its output becomes the ENet input for the next iteration. By repeating this cycle, newly formed wrinkles can be retained and existing wrinkles can become sharper, and the garment deformation gradually evolves into an elastoplastic behavior. The elastic network is an encoder-decoder structure. It split the body motion into two parts, a static component that captures the body pose, and a dynamic component that captures how the body moves over time. Each is encoded separately and then combined, along with the current rest bending, and fed into a decoder. The decoder outputs the garment's deformation for all frames, which is then applied through skinning to fit the garment onto the moving body. During training, ENet also compute the rest bending target for training plastic network. But during testing, only the predicted deformations are used. The plastic network predicts how the garment's rest bending should update over time, which allows newly formed wrinkles to stay and existing ones to sharpen. PNet takes the garment state encoded on the hinge graph as input. A graph-based message passing network models the spatial interactions between neighboring hinges. This allows the model to capture how local geometric relationships influence the evolution of bending along the cloth surface. The encoded features are then propagated through multiple message passing steps to aggregate information across the hinge graph. This enables the network to reason about larger spatial regions where wrinkles may form and interact. During training, the predicted rest bending is used in a rollout procedure to simulate the cloth dynamics and compute the loss against the ground truth sequence. During inference, the decoder directly predicts the rest bending from the propagated hinge features. Together, this architecture enables PNet to learn the spatial mechanics that govern the formation and persistence of cloth wrinkles. We use the AMAS-ACAD dataset, which contains the SMPL body model and hundreds of motion sequences covering a large variety of poses. We employ a physics-based simulator with a perfect plastic model as the ground truth. To highlight our model's unique ability to simulate persistent wrinkles, we also compare our model with the state-of-the-art self-supervised neural cloth simulators, PBNS, SNUG, NCS, Hood, and SENC. We have evaluated our model using a wide range of quantitative metrics, which are fully reported in our paper. Here, we focus on showing the visual results. When we look at the PBS result around the abdomen, we can see that when the body bends, the garment in that region follows the motion and undergoes a significant bending deformation. Because of the garment's plasticity, this bending creates persistent wrinkles, meaning the wrinkles before and after the body's bend should look different. Our model captures this behavior very well, while the other self-supervised methods fail to show this effect. We can see that PBNS, SNUG, and SENC are unable to generate wrinkles after the body bends. NCS, on the other hand, creates wrinkles even before the bending happens, and those wrinkles neither deepen nor evolve afterward. Hood produces wrinkles in the wrong locations and also fails to show any persistent wrinkle behavior. Since our PNet takes hinge graph base feature as input, its predictions are not affected by the specific garment mesh. As a result, our model can also generalize to different garment types when predicting the rest bending. We can see that our model consistently forms persistent wrinkles across multiple garment types, including the t-shirt, vest, trousers, dress, and long-sleeve garment. By observing the deformation of the vest during motion, we can see that our model produces results closest to PBS. PBNS, Hood, and SENC failed to generate any wrinkles, while SNUG and NCS produce noticeable wrinkles even before the deformation occurs. For the trousers, we conducted the same test, and again our model produces results closest to PBS. This time, PBNS fails to handle collisions correctly. SNUG creates wrinkles before the garment deformation happens, and NCS is unable to maintain the wrinkles. Hood and SENC also show wrinkle-like patterns, but the locations of these wrinkles are incorrect. Our model also generalizes well to long-sleeve garments. As the arm bends, the sleeve region tends to form persistent wrinkles, which is consistent with the behavior observed in the PBS results, whereas both PBNS and NCS fail to maintain such wrinkles. We also evaluate the generalization ability of our model across different body types. The comparison shows that PBNS and SNUG fail to properly handle collisions, while NCS produces wrinkle patterns that remain unchanged before and after the motion. Hood and SENC also exhibits no signs of persistent wrinkles. Although an obese body shape tends to stretch the garment and make wrinkles less prominent, our model is still able to capture the subtle plastic deformation of the cloth. In PBS systems, control the garment's physical behavior, usually done by adjusting physical parameters. In our method, we introduce a new tunable parameter, the yield strain. Here, we show the persistent wrinkles generated in the same motion with yield strain set to 30 degree, 60 degree, and 90 degree. When yield strain is 30 degree, like paper, the wrinkles are very noticeable and is very likely to form wrinkles after a bending motion. After increasing yield strain to 60 degree, the garment forms fewer wrinkles. And when yield strain is increased to 90 degrees, the wrinkles become much less apparent, since much more deformation is required before plasticity occurs.